All right, here we are for the final lesson in the number and algebra topic in this course. And this being the last lesson, expect it to be a bit of a challenging lesson to get through. And obviously none of this will make any sense if we haven't first looked into the previous lesson, which is introducing what an eigenvalue and an eigenvector is. So assuming that's down and you've had a chance to look at that and practice that, let's look at this first example. So I have this matrix A, which we saw actually in the last question. Sorry, the last notes. And in the last lesson, we were able to determine it had two eigenvalues, 3 and 7, and therefore each of those eigenvalues has numerous different eigenvectors, but one example of each was 1 and -1 for the first eigenvalue, and 1 and 3 for the second eigenvalue. So the first thing I want to do is rewrite this matrix A in P times D times P, where P times D times the inverse of P, where P are the columns of the eigenvectors, and D is a diagonal matrix with the eigenvalues. So the order we write these matters. And we have a choice, but once we decide on what we're going to do, we've lost that choice. And so for A, first, for matrix P, I have to have my two vectors. And I'm going to go in order 1, -1, followed by 1 over 3. So 1, -1, 1 over 3. Keep in mind from last lesson that there's an infinite number of eigenvectors for each eigenvalue, and so I don't have to use these, but these are the ones I'm using. All right, so that is my matrix P. Now that I have in that order, keep in mind this was for eigenvalue 1, this is for, let's make that look less like an X. This was for eigenvalue 1, this is for eigenvalue 2. So now for my matrix D, that's a diagonal matrix, so a nice clean, 0, 0 there, but just something over here and here. Those values have to now match up. So if I went with this first part here, whoa, that's a big marker. Easy tiger. Okay, if I chose that, which was from eigenvalue 1, then I need to put eigenvalue 1, which was 3, into this first blank here. And then 0, 0, it's always a diagonal matrix. And then since this corresponded to the second eigenvalue, I need to put that right here. Keep in mind, if I chose to write these eigenvectors in a different order, then I need to write that 3 and the 7 in a different order. So there is matrix A, here's matrix D, and the last part is the inverse. Oh, I'm already saying things wrong. Take that again. Here's matrix P, there that I have highlighted in yellow. Matrix D is highlighted in green. And then lastly, I have the inverse of P, which our GDC can tell us quite quickly. And while we have learned enough to determine the inverse of a 2x2 matrix without a GDC, even then it's still quite time-consuming. You want to find the determinant, and again, you're fine to use a GDC. And I would literally just type in this matrix and raise it to the power of -1, and you should get this. 0.75, -0.25, 0.25, and 0.25. And so this here, it's hard, I don't blame you for not being able to tell, but this here is equivalent to this matrix A. And I would encourage you, if you have time, to just double check. Just type these three matrices, actually really just these two matrices, into your GDC. And then just go that times the inverse of your first one. And it should spit out that right there. All right, let's clean this up a bit. Okay, now any 2x2 matrix can be written in this form. Once we know the eigenvalues and eigenvectors, any 2x2 matrix can be written where we have a matrix based on the eigenvectors multiplied by a diagonal matrix based on the eigenvalues multiplied by another matrix based on the inverse of this first matrix. All right, well, let's table that for a moment. And now let's just look in general. If I have a matrix, a square matrix to the power of 4, I want to show that it's the same as P times D to the power of 4 times the inverse of P. But only the diagonal matrix needs to be raised to the power of 4. So how can I show that using matrix multiplication? Well, A to the power of 4, if it's the same as this, Well, keep in mind, A we just saw is the same as P times D times P to the negative 1. That we saw is the equivalent of A. Well, if I'm raising to the power 4, I just need to do that 4 times. P, D, P, twice, 3 times. Oh. 4 times. Okay, so that said, if we look at this, notice we have these pairs of matrix, the inverse of P times P. We have that 3 times, which means each of those parts I've highlighted in green. When you multiply a matrix by its inverse, you get the identity matrix. So I can really just write this as P times D times I times D times I times D times I times P to the negative 1. Each of those parts I've highlighted in green is equivalent to the identity matrix. Well, now realize as well, I didn't write it out quite. I need one more D here. There we go. And so every time I multiply a matrix by an identity matrix, nothing changes. So really, I can now write this as just P times 4 of these D matrix times itself in a row, multiplied by this, and now we can see, yep, this is the same as P times D to the power 4 times the inverse of matrix P. So with that said, any matrix, any square matrix, I could write like this. And so since we already have this up here, right, this is P, this is D, this is the inverse of P. If I want to take this matrix here and raise it to the power 4, one way of doing that is to understand that I can just take this and just raise that to the power 4. And that's what it says here, right? A to the power 4 is a product of 3 matrices without any exponents. And so I'm pretty much just going to take what I have here. But instead of this part right here, remember when you have a square matrix, that is a diagonal matrix as well. Then when you raise it to a power of anything, I can just quickly raise each of these individually to the power 4. So it's going to look the same as this. And then all I got to do is evaluate 3 to the power 4 and 7 to the power 4. So putting it all together, my 3 matrices will be 1, 1, negative 1, 3, times 3 to the power 4, which is 81. And the other element is 7 to the power 4, which is 2,401, times that inverse. And so keep in mind this here, this is that same matrix P. This is the inverse of that matrix P. This here is that diagonal matrix of eigenvalues raised to the power 4. And if you were to check on your GDC and you were to multiply all this out, you would get the exact same value as this matrix A raised to the power 4. All right, and that's the easy part. All right, let's look at a applied question that broken up into a few parts. So first, there's 2 supermarket chains in a city, Supermart and Grocery Co. Each month, 14% of the customers from Supermart switch to Grocery Co., and 3% of the Grocery Co. customers switch to Supermart. So every month, there's a bit of a change between these. And initially, there's 3,700 Supermart shoppers and 2,500 Grocery Co. shoppers. So first, let's just think about what's happening after 1 month and show that these values here are correct. So let's start with Supermart. So think about Supermart. We have 3,700 customers at first, and it says that 14% of them go to Grocery Co. So that means they lose 14%, which means they keep 86%. So after a month, I can take my initial amount and multiply by 0.86, because they do keep 86% of their customers. Okay, but there's a bit more. Because while they lose 14% of their customers to the other company, they do gain 3% of the customers from the other company. So I need to also take 3% of the 2,500. And so in 1 month, we lose 14% and we gain 3% of the other company. And if you multiply this together, you will get 3,257. So confirming that's correct. And same idea here for Grocery Co. I'll write in the same order. For Grocery Co., they take 14% of Supermart. So they take 14% of this 3,700. So I can take 14% of that. Plus they have their own customers. They have 2,500, but they do lose a little bit of them. Remember, 3% of them went to the other company, so they still keep 97%. And if you calculate this, you indeed get 2,943. All right. So now the idea is, what if this repeats month after month, this loss and shifting of customers from one company to other, but they're kind of going back and forth. It's actually deceivingly complex once we want to start moving past this. So what I want to do is I want to summarize this change as a transition matrix, and then I can apply that to go to multiple months. So, and I want to call this transition matrix T. So how can we figure that out? Well, first, let's look at what we have up here and think about how we got these values. So I have matrix T, and it's going to be a 4-element or 2x2 matrix. So let's think about how I did this, okay? In which I have some matrix that's going to take into account all these shifting percentage amounts times our initial amount, so which was 3,700 for Supermart and 2,500 for Grocery Co. And it should lead to these values we got, 3,257 and so on. So what I want to do now, where that question mark is, this is the key part, how can I summarize what I did up here? Well, let's look back at here. First, I took 3,700 times 0.86. So in terms of matrix multiplication, what's going to go for these blanks, I can show it as, okay, so this times 3,700, that means this must be 0.86. Plus, it was 2,500 times 0.03, which means it must be this times 2,500, which means that next blank must be 0.03, and adds to this number here. And if you're not sure, it's great to be not sure, just double check. This times this plus this times this equals that. And that's exactly what we did in the last question. All right, so now let's look at the other company. What did we do here? We took 3,700 times 0.14, so this is going to be this times 3,700, which means this first blank must be 0.14, plus 2,500 times 0.97, so plus this must be 0.97 here. And again, it's good to be unsure, just double check. 0.14 times 3,700, yep, plus 0.97 times 2,500 equals 2,943. All right, so a big part of this question is done. Let me clean up all my highlighting here. This part right here we call a transition matrix, and I'm going to call it T. And essentially, every time I multiply by this matrix, I see what happens is all these customers shift around. And so if I multiply the initial amount times T once, I get this. That said, if I want to find how many shoppers are after 2 months, all I need to do really is take this transition matrix and just multiply by it one more time. And so a few ways of doing that. You can use your GDC as much or as little as you want. It's probably helpful here. So if I'm calling this matrix T, well then if I want to find after 2 months, I can just take T squared times 3,700 over 2,500. Or I can take that matrix and just be more explicit. 0.86, 0.03, 0.14, 0.97, raise it to the power of 2, which again, once you type it into your GDC, that should be quick to do. Multiply this by this vector, this 2x1 matrix, and you should get, either way you look at it, you should get about, I'll write to 3 significant figures, about 2,890 over 3,310. Keep in mind, this represents, after 2 months, the number of customers at Supermart. And this represents the number of customers at Grocery Co. And if I want to find after 3 months, I just make it a 3 there, or make it a 3 there. And you can use your GDC as much as you want. However, that's not the only way, but that is pretty quick once we have that transition matrix determined. However, we can also bring this back to eigenvalues and eigenvectors. And so this here will require our GDC less, but still requires it, but it really requires an understanding of eigenvalues and eigenvectors. So first, let's find the eigenvalues and eigenvectors for t. So let me write down that transition matrix again. Oops. All right, so if I want to find the eigenvalues, while these are not whole numbers, it's the same idea. I need to find the solution to where the determinant of, in this case, t minus the eigenvalue times the identity matrix equals 0. Now with that said, this is the main part of the last lesson, so I'm not going to go through every step. You should fairly quickly get to this matrix here, which is t minus eigenvalue times I. So in this case, 0.86 minus an eigenvalue. The only difference about this compared to what we did in the last lesson is just these numbers, since it's an applied question, are not whole values. I need to find the determinant of this, which is this times this minus this times this. I need to make that equal to 0. All right, now in this case, I really don't feel like expanding and simplifying all these because the decimals are fairly messy. I'm using technology anyways, so why don't I just solve this equation by graphing or some other way, but by graphing is a pretty nice way of doing it. And so I would graph this, which is a quadratic function. It's fairly a little bit messy, and we'll want to think about our zoom settings and adjust them a bit and find its x-intercepts. And it shouldn't take you too long to get 2 x-intercepts, which means 2 solutions for our eigenvalues, which makes sense. One eigenvalue should be exactly 0.83. Our other eigenvalue should be exactly 1. So we got our eigenvalues. So now I want the eigenvectors, which, keep in mind, while there are exactly 2 eigenvalues, each of these has an infinite number of eigenvectors. How do we find those again? Well, I now need to find, for each of these, I need to find the matrix of, in this case, t minus this times the identity matrix. So if I focus on, maybe I'll do this up here. If I look at the eigenvalue 1, which is 0.83, I want to start by taking my matrix here and from it subtracting 0.83 times the identity matrix, which is a bit messy, but shouldn't take you too long to get to 0.03, which again is just 0.86 minus my eigenvalue. This should be unchanged, this should be unchanged, and this should be 0.14. And now I need to solve this times a 2-element vector, and I want to make this equal a 0 matrix. And I should quickly get the 2 equations that are equivalent. In this case, 0.03x plus 0.03y equals 0. That's all I really need. You could always confirm that the other one's equivalent, but I don't feel like it. Which means I can see right here that 0.03x must equal negative 0.03y. Let's divide both sides by 0.03. That means x must equal negative y. And so one possible column vector for this would be anything where x and y are opposite. So how about 1 and negative 1? So that's going to be the eigenvector I'm going to use for this eigenvalue of 0.83. Let me now look at the other eigenvalue, which was 1. And so let me do that right here. I'll do it right here. Same idea. I need to take this and subtract 1 times an identity matrix, which is to subtract an identity matrix from it. And so I should pretty quickly get to this, negative 0.14, and so on. And then I'm going to multiply by an unknown vector to get my zero matrix. In this case, I get two equations that are essentially identical right away. And the first one I get is 0.14x plus 0.03y equals 0. A little bit messy here. If I isolate, if I solve for y, I pretty quickly get to y equals, as a fraction, I get 14/3 for x. The reason I want to stick with a fraction is then I can see I need to create an eigenvector from this. And if I write this as a fraction, I can see, okay, if I make x 3, y is going to be 14/3 of that, so y is going to be 14 exactly. And I want to give myself easier numbers. So I want to use x being 3 times 14/3 is 14. And so when I have an eigenvalue of 1, the eigenvector I want to use is this. Okay, and I did that pretty quick. So now I can actually answer this question, which is, let's write this transition matrix in this form, like the last question. Now we've done all this work. So I've just run out of space. I'll write over here. I have T equals P, remember, is the matrix of my eigenvectors. And I can choose the order. I'm going to put this one first, 1 over negative 1, this one second, 3 over 14. Keep in mind, these are not the only possibilities. Next, I need to multiply by D being the diagonal matrix of the eigenvalues. And so since I started with this vector, I need to start with this eigenvalue right here, 0.83. And then the other eigenvalue of 1 has to go here. And then finally, the last part is the inverse of this, which I can find on my GDC quite quickly. The decimals are pretty messy, so if you turn them to a fraction, which you should be able to do in your GDC quite nicely, you get, what I think is a bit nicer, you get 17ths, which are pretty nasty decimals, but as fractions, they're not too hard to write out. All right, so this here is equivalent to that transition matrix we came up in the previous one. The advantage of this is if I want to raise this to a higher power, I can just raise just this here, this identity matrix. Or sorry to say identity matrix, this diagonal matrix to whatever power I want. So the question asks for 6 months from now. All I need to do is take this and raise it to the power of 6 times my starting amount. And then I'll have my answer. And again, while it's still, I'm not saying it's easy, we've definitely done the bulk of the work. So let me just kind of finalize that here. So after 6 months, I need to take again, I'll basically copy out what I have already done, just to waste more of your valuable time. And every time I multiply by these 3 matrices, it's the equivalent of multiplying by that 1 transition matrix. And so if I multiply this by my starting amount, which was 3,700 for Supermart and 2,500 for Grocery Mart, this here, if I was to do this on a calculator, it would just confirm what we did in the very beginning of the question. This will just give me the same work as this, or what I did right here. But if I want to do it for multiple months, 2 months, I would put a 2 here. 3 months, 4 months, I want 6 months, so I just need to put a 6 there. And that's the most important part right there. That's it. If you actually do that, you get approximately, after 6 months, 1,946 for Supermart, 4,254 for Grocery Co. And I would also confirm, because if you didn't have to, if we weren't trying to write it in this form, right, that you were asked right here, if you weren't trying to write it in that form, then I could have got the same answer by just going back to this work right here and changing this 2 to a 6, which your GDC can do quite nicely. And you should get the same answer we just did. Keep in mind, as always, the purpose isn't just getting to an answer, it's understanding different approaches. And like I said, this very, very last lesson in this big topic in this course on number and algebra is pretty abstract, but hey, we're done, and I can stop talking.